Alrighty guys, welcome to the day 5-6 notes. Today we are talking about what's called a scale factor. Basically all that is we're just going to end up taking a shape and making it larger by some proportion. So what we did in class, and if you're doing this at home, you may not have access to a protractor. Feel free to ask your teacher to borrow one. So I'm just going to kind of draw it by hand here because you'll still understand the concept. So ultimately what we have here is with your protractor, you construct triangle ABC with a base of 3. So this is A. Let me actually get the marker out here. So this is A, B, and this is going to be C. This ends up being 3. This ends up being 4. And then we had to actually measure the length of segment AC. Okay. Let's see. AC. Time out. Let me gather my thoughts here. There you go. Sorry, I had A and B switched up. So AB is 3, AC is 4, and what it asks for first, let's just go through this down the line. It wants us to find the area first. Now, if we want to find the area of a right triangle or any triangle, it's going to be 1/2 the base, 3 times the height of 4. So that's going to be 1/2 of 12, okay, which comes out to 6 square units. And if we are actually measuring this, like we did in class, the units we can fill in as inches. So this is 6 square inches. So our area came out to 6 square inches. Now the measure of segment BC, that's this guy right here, we could actually take out the ruler and measure that. Or, if you don't have access to a ruler, you could do 3 squared plus 4 squared is equal to C squared. Go through and solve using the Pythagorean theorem. Okay, so it's going to look something like this. So 25 is equal to C squared. And when you take the square root of both sides, you get a length of 5 for C. Okay, so our length there, measure of segment BC, is going to be 5 inches. Now your perimeter is just simply going to be all 3 sides added up. So that's 3 plus 4 plus 5. Okay. And let me see here. Not sure what's happening. 3 plus 4 plus 5, and that comes out to 12 units. Oops, not units, because we've actually designated a unit of measurement. So that is going to be inches. Okay, 12 inches as a perimeter. Now next, measure of angle B. You would have to go back and review the day 3-4 notes on how to measure angles. But angle B comes out to approximately 37 degrees, and angle C should come out to approximately 53 degrees. You would need a protractor to do that. Again, go back and review measuring with a protractor if needed. Okay. So again, today is based around scale factors and taking a shape and, in this instance, doubling it in size. So what we're going to do is we're going to take our original shape, the 3, 4, 5 right triangle. Let me just sketch it here for our reference. That was A, B, and C, and this was 3, 4, and 5. Okay, and what we're going to do is we're going to take X, Y, Z, and we are going to double it in length. Okay, so we're going to have a base of X, Y. We're going to raise this height up here, and it should be labeled Z. So if we double 3, what does that become? Well, pretty straightforward. That becomes 6, right? So our old base of 3 becomes 6 if we double it in size. Our old height of 4 now becomes 8. And using logic here, then this should be 10. And we verified it in class with a ruler, and it actually worked out. So our area here is going to be 1/2 our base of 6 times our height of 8. Okay, and that is going to be 1/2 of 48. So our area in this case was 24 square inches. Okay, now let me go back and label this again correctly. So it has X, Y, and this apex up here at the top of the triangle is going to be Z. Okay, that Z is right up there. All right, now if we want the measure of segment YZ, again, we just showed that was 10. Again, you could use a ruler to establish that. You could use Pythagorean theorem. You can go through and do 6 squared plus 8 squared is equal to C squared. When you go down and solve for C, C ends up equaling 10. But then also if we just double 5 here, that becomes 10. Okay, so our perimeter is 6 plus 8 plus 10. You just add the 3 sides. And that comes out to 24 inches. All right. Now, this is what was interesting here. Students in class, several, thought, okay, well, if before the measure of angle B up there was 37 degrees, then this right here should be double 37 degrees or 74 degrees, right? And they went in, they measured and realized that, no, it's not 74. It's actually still 37 degrees. And the measure of angle Y was not 106 degrees, which actually wouldn't make sense because that's an acute angle, right? It's not greater than 90. It was actually still 53 degrees. And this 90 obviously is still 90. So we doubled the sides, 6, 8, and 10, but the angles all stayed the same measure. Pretty interesting. Now, same type of thing happening here when we tripled the sides. Okay, so when we tripled the sides, this guy that was 3 becomes 9. This side that was 4 becomes 12. And this side that was 5 is now going to become, 15? Okay, so if we triple the sides, this is 9. Again, let me get the marker out. This is 9. This is 12. And this comes out to 15. And you could also confirm that using Pythagorean theorem. 9 squared plus 12 squared is equal to c squared. And I can promise you if you work through it and solve for c, c ends up equaling 15. Okay. Now as we go through and we solve for area here, and we do 1/2 the base of 9 times the height of 12. 9 times 12, let's see, that's going to come out to 108. Okay, and 1/2 of 108 is 54 square inches. 54 square inches. Segment ST, this guy right here, and again, I'm realizing I didn't label my my vertices. This is R, this is S, and this is T up here. Okay, T is right up here at the top. The measure of segment ST is 15. Okay, again, we measured it. We know proportionally, if it's triple the size of the original side of 5 up there at the top, it becomes 15. And again, just to triple check, Pythagorean theorem also proves that it's 15. If you add these 3 sides, 9 plus 12 plus 15, 9 plus 12 is 21. 21 plus 15 is 36. This comes out to 36 inches. And once again, we realized that the angles stayed consistent. So what we summed up here in class was this. Similarities between the triangles. Let me start a text box here. The angles all stayed the same regardless of the size of the triangle. Okay? They all stayed the same regardless of the size of the triangle. Now, differences between the triangles, the area and perimeter got larger as the sides got longer. Okay, so something along those lines, and you may come up with some more similarities and differences. Like similarities, they each have 3 sides. They each have right angles. There's all kinds of similarities that you guys can come up with here. And there are several differences as well. Those are the main ones that we're looking at. So now here, all this is just kind of going through and backfilling information from the pictures. So I'm going to do that real quick. Why don't you give it a try also? And then we'll come back in just a second here. So pause it right here, right now. All right, so it should look something like this once you fill it all in. We have 3, 5, and 4, 6, 10, and 8, 9, 15, and 12. Again, you're just filling in the sides from the problems up above. Perimeters and areas you're also throwing in there from what we calculated above. Now here's where it gets interesting. We have the ratio of the perimeters for XYZ over ABC. That's 24 over 12. The ratio of the triangles RST and ABC, that's 36 over 12. That comes out to 3. And that makes sense, right? Because the ratio of the perimeters here, we just doubled it in size. And here we tripled it in size. Okay, but what you recognize here with the areas is that when you double the sides, the area more than doubles. And when we tripled the sides, the area more than tripled. So when we doubled the sides, it went up not by double, but by 4 times. When you triple the sides, it goes up by more than 3. It goes up by 9 times. So what we made the connection in class here was if you double the sides, it doesn't go up by double an area. The area goes up by whatever the ratio is or scale factor is squared. Here it goes up by the scale factor, in this case 3 squared. So the area goes up by 9. So if we follow that same logic, if we take this scale factor of 3 over 2 and we square it, check it out. 3 squared is 9, 2 squared is 4. So the area more than doubles. It goes up by the scale factor squared. Okay, so you might want to add a little note there. Area goes up by scale factor squared. Okay, not just by the scale factor like the perimeter did, but it actually gets bigger faster. Okay, that's what's called a quadratic. You're going to learn more about that in IM2. That is a quadratic sequence. Okay, now for the scale factors here, what do you think the scale factor was between ABC and XYZ? Well, the scale factor is just going to be 2. It doubled in size. And the scale factor between ABC and RST is 3. It tripled in size. Now down here, for each set of 2 triangles, how do the ratios of corresponding sides compare? Well, let's look at triangle XYZ. XYZ right here. Okay, triangle XYZ is on top, and we have ABC down here on bottom. So if we set up the corresponding sides, 6 corresponds with 3, 8 corresponds with 4, 10 corresponds with 5. Each of those reduce to 2, 2, and 2. So it's the same. For each set of 2 triangles, how do the ratios of corresponding sides compare? It's equal to that scale factor again, right? Now over here, we have RST over ABC. Okay, RST, triangle RST over triangle ABC. And the same thing is happening here. 9 over 3 reduces to 3. 12 over 4 reduces to 3. 15 over 5 reduces to 3. And the same thing is happening down here with the ratio of the perimeters. The ratio of, let me get this out of the way, XYZ over ABC is the same. It's the same as the scale factor. That becomes 2. And then same thing over here, RST over ABC. The ratio of the perimeters is also the same as the scale factor, 3. Now, if we look at the ratio of the sides and comparing it to the ratio of the areas, the ratio of the sides was 2 here for ABC, right? ABC to XYZ. Let me get this out of the way again. ABC to XYZ. Let's actually write this the correct way. Okay, we had XYZ on top. Okay, so we had XYZ over ABC. That was equal to the scale factor of 2. But the ratio of the areas came out to 4 because we took the ratio of the sides and we squared it. Okay, now over here, RST to ABC. Remember the scale factor of the corresponding sides was 3, but we had to take that and we had to square it, and that gave us 9. Okay, now lastly on example 3, if you don't have a protractor, you'd struggle with this a little bit doing it at home. Well, you wouldn't be able to do it at all. So again, ask your teacher to borrow one if you'd like to go through this just to make sure that you're all set on it. What we did in class here was we drew a segment that was 2 inches long, and then we constructed some angles here at 110 degrees. Okay, so they both looked like about that. Okay, let me make this a little cleaner. Let's move this over a little bit. Okay, not going to let me. So we'll say this is 110 degrees and this is 110 degrees. So this is not a triangle, right? And what we realized in class here was that this guy was a trapezoid. All right, so that came out to 110 and 110. Let's see here. We made AB here, and we constructed AC so that it was 3 inches long, and BD so that it was 3 inches long. And we all measured the length of CD, and it came out to about 5 inches right here, about 5 inches. Okay, just some practice constructing there. And then what we did was the same thing, just to reiterate the point in this grand finale here, that you can double the sides, making this base 4 and these two sides 6 and 6, and with 110 degree angles, and this would come out to 10. The angles would remain the same, but the sides would just double. And that was about it.